Okay.
Okay. So I guess where we left off last time, we were going through the dog bone presentation, looking at the material testing and how to read the chart. What we'll do today is we'll kind of go through that activity and show you how we walk through it. And there's kind of like two versions of it. So depending on if you have the structural stress analyzer or if you're going to do the virtual tensile testing. So we'll kind of show you both patterns there. Then we're going to move into the stress strain problems, and then kind of call it a day there and try not to get too far ahead. So let me share my screen here. Hopefully that's working. In Unit 2, underneath Lesson 2.3, what we're going to take a look at here is the 2.3.2 simulation for the tensile testing. So if you want to open that document up and follow, you can. There's also a presentation that goes through. Now this one is if you have the structural stress analyzer. So that's that machine that we bought years ago, or you still can currently buy, just a little bit more expensive. And then the activity that would go with that version, it's the same activity, it just links up with the structural stress analyzer. So it would be this activity right here. So I'm going to open up this one right here. And we'll take a look at that. So 2.3.2 goes through the simulation mode, and it's kind of nice. If you need like a quicker activity, if you don't have time to build the dog bones and actually break them, or if you don't have the machine, there's an application online that you can go to, which is just the virtual tensile tester, which they list here somewhere. And I think it actually has the ability to, you can download it, but all I do is I go onto the internet, I go onto Google, and I type in virtual tensile tester, and it pops up. And what it does is it gives you a couple of different materials here that you can test. So you just grab it, put it down into those little clamps, hit start. It breaks it, shows you kind of how the graph is built, and then eventually it snaps, kind of anticlimactic. You can put in different samples. So now I have an aluminum. We can see how the chart changes. The graph is not quite as defined here where our yield point is. Put in another one. Oops. The cast iron. You notice cast iron doesn't really have much deformation. It's going to kind of pull and crack very quickly. And then you have copper. And that one's going to give you much more deformation. So what you do is you have the students kind of play around with this, and then have them choose one of the three different materials. And I say three because the cast iron, because it doesn't really have a large deformation, I would say don't use that one because it's really harder for them to do the math that we need to do here. So one of these three, doesn't really matter which one you choose, just whichever one they feel comfortable with, or divide the class up into that, a third of the class takes one, a third of the class takes the other, and so on and so forth. So once you figure out which one you're going to take, build the chart, and then what we're going to need to do is actually we're going to need to grab this piece here. So what I use is the snipping tool, which just comes preloaded here, and I just grab the chart. Okay, and then I can go back to my document, and then what I'm going to do here is go through and paste that chart in here. I think it's 7 times. So anywhere in here where it says insert test graph here, you can go ahead and just put that test graph in there. And this is pretty much the same thing in the SSA version, the machine version. You'll get a graph just through a different program, and you'll do the same thing. You'll copy paste it into this file. Okay, easy enough. And the reason why they want you to copy and paste it in multiple times is because we're going to identify those different parts or different points, excuse me, on the graph for each of these different things. So for example, the proportional limit stress, which we went over last time, the students should know what it is, but they should also now be able to figure out what where it's on this graph and to be able to identify the stress that's being experienced at that point. So what they'll do is they'll figure out, okay, here I've got a slope on this line, so I know that's my elastic region. I know that's my the slope of that line would be my modulus of elasticity. And I know right up close to the top is where my proportional limit is. And the student should be able to figure that out because they know that at the proportional limit, that's where proportionality ceases. So they can see that there's a constant increase in force and a constant rate of stretch, if you will. So if I add 5 pounds, it stretches 1/1000th of an inch or so on and so forth. So they're going to use this point here, which is at the 20 kilonewtons rough range, and they're going to figure out what the stress is going to be there. Okay, so stress is going to be equal to our force divided by our area. So our force here is the 20,000 newtons, 20 kilonewtons, divided by our original area. And they have the original area up here. They have it listed for you as far as what the measurements are. So if we're using the millimeters, you can figure out what your original area is off of the metric. Or if you want to figure out what your original area is in the SI, it gives you that information right there. So at that point, I would take the 28 kilonewtons and divide it by that original area. Now, you'll notice that we're using the original area of the piece, so before it actually broke, as opposed to the area once it's broken. And that's kind of a standard that's used in material testing. They'll go through and, it's kind of difficult to figure out what the area is as it's being stretched. So they just use it as a standard to make it a little bit easier. Okay, so I've just seen here Trisha's asking if it's the, this is the actual form I use with the students, I believe is the question. This is the form that I use with the students, but I use the SSA version of it, but it's pretty similar. So all they do is they use the same area, they figure out where the next point is. So here I know the yield point's going to be just past my proportional limit, so they're using a force. They can kind of zoom in here if they have to and figure out what the next force would be divided by the area. So your proportional limit, your yield point stress is not going to be too different. It's going to be pretty close. Your ultimate tensile is going to be, find where the maximum force is divided by the original area. As we move down here, your breaking or rupture point for us is going to be all the way over here, and we'll divide that by the original area. I think the first 4 are pretty easy for the students. They can find the points on the graph by going back and forth between the PowerPoint and their notes. But then we get to the modulus elasticity, and you'll notice the formula here is a little bit crazy. It has F2 minus F1 times the original length. This is the delta 2 minus delta 1 times the area, the original area. And what ends up happening here is it's really just force times original length divided by deformation divided by, times area. But what ends up happening sometimes when you run the test, it won't happen on the virtual one, but if you're running an actual test, before the piece can actually get seated, sometimes there'll be some sort of slipping until it finally seats, and then it'll start adding force. And what might end up happening is something like this. So you might end up getting a chart or a graph that looks similar to this. So it starts to test, and it's really not adding the force. And then when we look at where our slope of that line actually follows, we're trying to basically eliminate this area or this original data. So by using this formula here, we can kind of eliminate that little stray data at the beginning and then get into our proper area where we'd find that slope of that line for the modulus of elasticity. For the most part, I just tell the students don't worry about it. Just take the force times length divided by the deformation times your area. I don't know, Karen, I don't know if you can hear me. Is that how you deal with it as well?
I'm back. I don't know what ice is affecting what internet, but we're back. Yeah, and we often get that little introductory, what I call data, non-functioning data there at the beginning when it seats, especially because my kids make their own dog bones. So we have sometimes they're not very straight by the time we've threaded them, and so we've got the little adjustment that takes place there. But my kids print one large graph that's a full screen, and then I have them, mark all of their important points on it. And so we talk about where's your data going to start, and I do what Adam does. I'm fortunate enough to have a stress analyzer also. So you don't get perfect data, but you do get interesting data. So.
Yeah, and I kind of like that even though you're testing the same aluminum or the brass, it changes a little bit just because, the one kid made it down to the exact diameter he was supposed to, and the next kid didn't. They made it a little bit different. Right. So it allows them to see what happens if you increase or decrease the diameter in your testing results. Then they go through the modulus of resilience, modulus of toughness, and again, the formula is a little bit screwy for the students. For some reason, they never understand what the heck YP stands for. For me, it's kind of, all right, put it together. What words do you know that begin with a Y and a P that we're dealing with in these calculations? So eventually you have to tell them, okay, it's yield point. So the stress at the yield point, which they solve for up at the number 2 problem, and then the strain at the yield point, which they haven't solved for yet. So they'd have to find that yield point and then figure out what the deformation is at that point, and then divide that by your original length to find the strain at that point. And if you look at it, this formula is basically finding the area underneath this graph right here. So if you drop the yield point straight down, you get a triangle. So this is nothing more than 1/2 base times height. Your stress being the height, your strain being the base, and then half being a half, obviously. And then the last is your modulus of toughness, and that's giving you this formula to solve for what's underneath the graph here. And again, a lot of times you have to tell the students, okay, BR is for breaking point, ultimate ULT. Once they get that, they're okay usually. A lot of times my students mess up the math here. They don't necessarily take the stress times 2 times or plus 2 times the stress of the other one. A lot of times they'll add it together and not do the multiplication. The other thing is, and Karen, you probably get this too, I'm imagining, because it happens quite often, but instead of them figuring out the strain at the yield point here or the strain at the breaking point, they just put whatever the deformation is.
Right.
So they just put
or the force.
Yeah,
whatever number data point they've got.
Yeah, for like the stress, they'll just put the force. They didn't actually go through and do the force divided by area. So you have to go back through it, and once you tell them, they realize their mistake. But right off the bat, there's a lot of times that they're going to do that. It's a pretty good activity. It really hits home the concept of this chart and how to read it and all the important parts of it, and then they can apply this down the road. Especially we get into our EDD course, the Engineering Design Development, the capstone course. Not every kid will do this, but they have to, well, in each of the projects, they have to do some sort of testing. And if they're doing, like we did a lift for a car one time, and they had to be able to test the metal to figure out was it strong enough to lift a car safely that somebody could go underneath it. Now our machine that we have only goes up to 1,000 pounds, so they had to kind of rig up a system to figure out how to test it, and then be able to read the chart that came off of it to say, okay, when I tested this at the rate it took to bend it, in this point right here was in my safety, my comfort zone. So that's where I knew that the car can come up on it, it'll stretch a little bit, but as soon as it comes off it, it's going to go back to its original state. And they needed to make sure that their testing didn't result in it being somewhere up here where it permanently deformed the metal. Then we knew it wasn't strong enough. They'd have to go back and re-engineer it, redesign it so that it would work properly. So it was kind of cool to take this and then stretch it a little bit further. It would be really nice to have a machine that you could test with where you get up to the 100,000 pounds, but those are very, very expensive, obviously.
I think the other thing that kids really confuse at this level is the fact that the stress strain graphs look so much like the force elongation graphs. And so I always have to ask them, do you have a stress strain graph? Do you have a force elongation graph? What graph do you have? And then denote that. And so it makes sense that they are similar in shape, because stress is going to be the version of force and strain is going to be the version of elongation, just the neutralized, where you can say it doesn't matter what size my sample was, I can compare everything of this particular substance, whether it was a great big dog bone or a little dog bone. But we have that. My kids want to go up and use the output like it's stress or strain versus force or elongation. So I make them write on top of every graph stress strain graph or force elongation graph. Now, it doesn't always fix the situation. They still confuse them. But just make sure they're aware, because sometimes you can just grab data off if you have the right graph. So just be careful that they are really similar. I'm trying to get to, and I don't know if you can, here we go, if you can turn the screen over to me here in a second. I'll show a video of, we had a kid who took one of our videos or took a video with his phone of the SSA ripping one of the bones and then slowed it down. So let's see if it will let me. Am I up?
There you go.
Okay, so pardon my email, but right now it's the easiest way to get there. So there's the metal sample in there, and you can see it starting to rip right there, and there's its break. It is honestly, for my kids, one of the coolest things they see or do. And so I'm not going to tell anybody how to spend their money, but if you can get an SSA 1000, I think it's money well spent. So
it's about like
just
$3,300, $3,500.
Yeah, it's a lot of money. But it's kind of an interesting grant. Like we'll have weird grants that we can acquire, and so it's like a piece of equipment that maybe you could write a grant for. My kids go through the process of over the past week. They've been coming in and out of. I just have huge, like 12-foot rods of aluminum and brass, and they've been cutting off 4-inch pieces. Over the last, today I have my last group use a grinder to grind off the ends and flatten them and then bevel them. And I had one group start milling out. I have a metal lathe in my room, start milling out the bone itself. And you guys will see in the modules in 2, I think it is, that there's a kind of a description on how some dimensioning on the dog bones. I've modified mine a little bit because I like mine to be 4 inches instead of 3 inches long, just because I find my kids can thread them easier. But again, it just, like Adam went through that manufacturing video, and it was so very cool. And I, ticked off the 10 things that we don't have in our school that I need to make that happen. But if if you have a nice machine shop in your school, then you probably have a metal lathe and, probably have a grinder, and you can accomplish a lot of that. I really started doing it because the samples were so expensive. And somebody kind of recommended that I invest. In 1 year, I can invest in a metal lathe and a grinder for the price of all the samples. And so the school was pretty excited to trade that in. So
yeah, and you can get like from Harbor Freight. I know somebody in the past that bought it for like $300. Yeah, they're not too expensive.
Mine's a Harbor Freight one, and it does its job for me. I wouldn't want to mill something out every day, but it does what I need it to do, which is, mill out 25 or so dog bones a year. I just replace the bit. So, and it's cool. I have a bunch of suburban kids that are super excited to have used a grinder and a metal lathe, and they haven't ever seen a tap and die kit, and so they know how things are threaded and stuff like that. So it's kind of fun to do that. Does anyone have any questions for Adam about the SSA 1000 before I kind of start talking about maybe the calculations that go with this? Oh, did the video not show?
I did
I
not
see
see
some
it.
people over there saying, you guys didn't see it at all? Are you seeing my screen at all?
We can see you, we just can't see the video.
You can see me. Can you see, is there a
We see your
231?
computer screen. We see your computer screen, but the video didn't come.
Oh, sorry. It was on my screen, so I was hoping that it would come through. I'll tell you what. I will attach it to an email and send it out. So, yeah, it's kind of just fun to see. It's not very long. It's about 10 seconds long. So, okay. Questions for Adam about
So
simulation
is
or go ahead.
is the SSA 1000? Is that something that's on that POE Excel spreadsheet that I had that I like submitted to my school to buy?
I believe it's still there,
Yes.
but it's not. If I remember correctly, it's not listed underneath POE anymore. I think it's like one of the extras. There's a
Okay.
option. Let me go look at that. I'll find that.
Okay. I mean, I got like 20 boxes in my classroom. I just have to open them up and try to figure out
It's
what's all in there.
it's huge. It's like the
Oh,
box itself is like 4 foot by
okay.
5 foot by 1 foot.
Okay.
You would know if you had an SSA
Okay.
1000 hanging out
Yeah.
All right. Thank you.
in your room.
It's not part of the bid anymore. I think because they're basically had to cut the cost of the curriculum in order to try to get into more schools. But it is listed as an optional thing to get. So it is in that workbook. There should be an optional section, which I'm going to check for right now to see what the actual terminology is for. But it will list that one.
Yeah, and it's, and like I said, if you have a university near you, or maybe even a metals lab, like a fastener production place near you, they will probably have some sort of stress analyzer. And so, if you can maybe do field trip, lots of birds, one stone, where you can get to go see that ripped and watch some of the other stuff that we were talking about in the manufacturer video. By the way, Adam showed that manufacturing assignment that he does, because I normally mind-numbingly try and dance my way through the 46 slides of the manufacturing PowerPoint, and I used that assignment, Adam, that you gave us last week, where the kids put the definitions in the pictures, and it was awesome, actually. It was really, really good. So I modified it just a little bit to fit my needs, but my kids worked on that today and got a lot more out of the experience than just watching me.
They didn't get a nap though, so.
I know. It's enrollment time right now, so I always hated doing that manufacturing PowerPoint. Like, go tell your friends how fun this class is.
Yeah.
Don't talk about this PowerPoint.
Yeah.
But no. Okay, so let's talk about the calculations that go with this. So what I've done is kind of dropped in this document without the question attached. It's just in the teacher resources, it's the answer key to 231. And so all I've done is, just for a few of them at least, I've dropped the question in. The document for the questions looks like this. 231 stress strain calculations, and then there is a worksheet that goes with this, a template. Are you guys not seeing my screen again?
No, I don't see your screen.
No, we just see the new meeting thing.
Okay. Adam, can you see if you can share with me again?
So you should have the presenter capabilities right now. Yeah. So we could see like your screen, but it wasn't updating. I don't know if you, maybe the one slide you had to minimize or something.
Okay.
See if,
Sorry,
can you
guys.
minimize that screen there maybe? The go-to meeting screen. I don't know if that.
No.
for
Okay,
whatever.
here's my theory. If I just go away, it's not because I'm not trying to be here. I know that you're thinking she has left so many times.
Like it had a web page open, right? It just said new meeting on it.
Yeah, I've got that too, and I can't. Hang on. No luck?
You're back,
Sorry,
yeah.
team. Okay, I'm going to try again. I tried something else. Does that show up? Do you guys see 231 yet?
Nope. No.
No. Okay, Adam, I may have to have you pull 231 up while I talk about it because I can't get it to grab my screen.
All right. The PowerPoint or the
No, the answer key,
answer key. Okay.
and it's in the teacher resources under files. Yeah, it won't let me grab this sharing option. Sorry.
Yeah, I don't know. Doesn't like you tonight.
It's, I know. I was like, I need to teach a class at school tonight. They're like, no, we're closing the building down. Okay. Or I won't be teaching a class tonight. Okay, so I need 231 if I could. There we go.
Okay.
So this is the resource in the teacher resources. So this is the answer essentially. The questions, the 231 questions themselves, come in a pretty compressed document. And you have that. And then this template that has this structure for kids is also available. I have some students who really, really like that template. Here's where the picture goes, here's where your formulas go. And I have some students that find it incredibly distracting. And so if you'd scroll down, sorry. So here are all those formulas we talked about. Adam showed us in the PowerPoint. They talk about a problem solving, basically, state what you know, state what you don't know, draw a picture of your situation, figure out what it is that you're trying to find. But so that's all listed here. So kind of the beginning of this packet is deep, but I think worth copying for the kids. And so it kind of walks through that. So here's where the questions begin. And you'll notice that they are pretty compressed. So there's obviously not enough room to do your work here on this PowerPoint, on this particular worksheet. I give the kids a couple of options. I make the worksheet that's in the format of the answer key available, and I make the this document available. And if they want to space it out and print it with spaces in it and work there, they may as well. So they need to show me all that information. They still need to list what they know. They still need to list what they're trying to find. They still need to draw me a picture. They still need to do that process, but they don't all love the template that comes with it. So this first question that we have says that we are looking for says the weight of an 18,000 pounds supported by a rectangular base plate that is 9 inches wide and 2 feet long. And immediately I ask the kids to underline the fact that they have two different units. We have inches and we have feet, so that's going to be a problem. The base plate rests on a concrete slab. Determine the stress that the base plate exerts on the concrete slab. And they asked them to express their answers in both pounds per square inch and pounds per square feet, and it asked for some precision on that. So I don't know if you could go over to the answer key for me. So this is what the answer key is going to look like. It is in the format of the template that they provide for the kids. Yes, Trisha, that's true. Stolman POE with a capital S and capital POE. So they list their knowns, they list their unknowns, they draw their picture, and to be honest, a lot of times that picture is some of their biggest issue, that they cannot figure out what they've got and what's being asked of them, and I understand that. So we talk about the fact that we have been given a weight, which they have identified as capital, a weight which they have identified as our force. And the kids will struggle with the fact that, unfortunately, we kind of waver back and forth between capital P and capital F. And I wish there was some consistency to that. And Adam, what do you, I mean, I always tell my kids that we're going to kind of have to work with the fact that the formulas in physics have both P and F for that.
Yeah. Right, it just comes from, where it really comes from is when they started building this curriculum, there was content from different people, and some people used P and some people used F, and then they just kept it.
Yeah, and so it's kind of travel between. My kids pretty consistently use F in place of that. So like my answer key to this would have a capital F as opposed to a capital P. But we've got a width of 9 inches, a length of 2 feet, which I would ask the kids to circle anytime our units don't match. I ask them to circle that. And we have a force of 18,000 pounds. What we don't know is the area. What we don't know is the pressure. What we don't know is the pressure. And so we have in our list of formulas, and Adam said he gives out kind of the master formula sheet to this. If you do that, maybe the first few pages of the question document aren't necessary, because they're basically a repeat of that document. It's got all the formulas and all, it talks about all the variables. So you can kind of make a call what you cut and paste and keep on that. So in this, you'll notice that the work is on the right. And so for some of my kids, the picture being in the middle is what they find really distracting. My kids, some of them that don't like this template, like to put the picture on the top. Then they put their knowns, then they put their unknowns. They list the equations that they're going to use, and then all of the work's going to be at some point identified. And so even for my students who don't use this template, they still have to have the labeling of what they have here. So we are looking for the pressure. We're going to go through the process of coming up with the area both in square feet and square inches, because they asked us both of those things. Really, once you have that, pressure is just going to be the force divided by those areas, and you're going to get 2 different units, and then you're going to round accordingly on this first one. So I kind of wish the first one didn't deal with pressure, because we've been doing so much work with stress and strain. It's not a terrible place to start, because it's not as problems go, it's not a very difficult problem. And can you go ahead and go down to 2? So question 2 says a 1/4 inch diameter rod, and notice that the 1/4 inch is the rod's initial diameter. And so like for my kids, that's what we start with, is a 1/4 inch diameter rod, and then we mill that out. So it's important that they understand that the 1/4 inch is not the location of the brake, because the brake's going to be milled out, it's going to be smaller than that. It's machined on a lathe through a smaller diameter that's used for a specimen and tension test. So it basically, they just created that dog bone. And if your kids have seen Section 232, that SSA, either the simulation or the real one, they'll know what that dog bone looks like. The rod material is expected to break at a normal stress of 63,750 psi. And you'll notice that that's stuff that's known on the left. And I tell the kids that's a gift. Anytime they give you stress or strain, they have handed you the formulas that you're going to use. And notice that we're in pounds per square inch. So any work we do now is going to have to be both in pounds and inches. If the tensile testing machine can apply more than 925 pounds of force to the specimen, calculate the maximum rod diameter that be used for this specimen. So one thing that I want you to notice,
Oops,
Adam, I
sorry.
think that's
Sorry.
okay.
Trying to find that information. Forgot I was on my screen.
No problem. One thing that I want you to notice is the diameter. It's in the bottom left corner here. When they talk about diameter on this, my kids are very used to pi r squared for area, and my kids are very good at working back and forth between diameter and radius. But in our problems that we have, they will often write area in terms of diameter. So they'll have pi times the quantity diameter over 2 squared, which is really then diameter squared over 4. And so the kids will see this weird formula. It's area equals pi d squared over 4, and they'll have no idea where it came from. So it doesn't bother me if the kids work through radius and then convert to diameter as opposed to using that formula. So just understand that that's where that comes from. And if they're looking at if you have an answer key, if you show this answer key on your protected website, then make sure that you understand that they're going to work through that. So we know that stress is the force over the cross-sectional area, and the cross-sectional area is the area of that breaking, so it's that skinny point. What we're trying to find is that diameter there. So they go ahead and they say we've got this stress, we've got the force, we're trying to find the area. They work through radius in this one, and then they work to diameter on that. So again, this one's not super hard once they understand where all the numbers come from. For me, I assign activity 231 and activity 232 in the same week. On the same day, I assign both of them. And then since I'm actually doing the physical stress analyzer, my kids are taking turns coming up and working on the SSA 1000 with me. And if you are not working on that lab, the 232, then you're working on these calculations 231. So everybody's got something to do. But I think you could do the same thing with the simulation where you said, that you're going to work through some of them, and they were both in place, because some folks are going to finish that simulation pretty quickly, and some folks don't. And so I've noticed that in my summer training, because we do the simulation, the summer training. I have an SSA 1000 at my summer training program. I put both of these out there for them to work through, so they're kind of both in their hands at the same time. And if you want to scroll down, we'll do one more. We'll look at number 3. Number 3 is a good example of where they use area equals pi d squared over 4. So if you look in the top right corner of this solution, they're getting pi d squared over 4. I have the kids work these on their own. They turn them into me, and I grade them for accuracy, and then I turn them back to them, and we go through them for corrections.
Yeah, I like to do like, I do like, one or two with them. I choose some of the ones that might be multi-step, so we can kind of work through them, and so they kind of get the process down, and then they'll work through them in their engineer's notebook. But sometimes you have to worry too, because even though these files aren't supposed to be out there on the internet, some of them are wise to it, and they'll Google search the answer key, and they'll find it.
Yeah. One of the things that my teaching assistant does is my aide, basically, is they're responsible for, whenever we get to a new activity, going out and trying to find the answers online. And so then I'll know where the answers, if they're out there, and then I just turn them in the project lead the way. And that pulls them off a little bit. If I can keep ahead of it a week or so, it'll get them off somewhat. But Adam's right, they're out there everywhere. But it's easy to tell when they copy these, actually, because they copy the picture exactly.
Yeah.
And I don't draw these pictures exactly. And so if you look through this document and you see kids that have these exact pictures, you will for sure know that they copied them. Like on number 2, there was that picture of that dog bone. That's like a dead giveaway that somebody found the answers and copied them. And my kids keep their notebooks. So some of my kids just, it's hand-me-down. Somebody will hand their notebook off and they'll have answer keys. So, you know, consequently, it nails them when they're on the test. But they'll go through and work these. I'll grade them. We'll come back around. They get points for correcting them. They can't get all the points back, but they can get quite a few of the points back for going through and doing corrections with me in class. So this example number 3, the question at hand on this one asks about determine the maximum load a 1/2-inch diameter steel rod can support if the normal stress of the rod must not exceed 24,000 psi. So super nice. There's not a lot of stuff that they've given us, but it's easy to find out. They gave us stress. They've talked to us about the diameter of the rod. And so you'll notice over on the right side when they have area, that pi d squared over 4 shows up, which is fine. I let my kids use radius instead if they want, as long as they're going to convert when all is said and done. But they substitute in the diameter we know, we find the area. Once we know the stress and we know the area, it's easy to find the force. Again, they request some rounding, so be ready for that. One way you can also catch kids is if you go through and modify the question not to have the same rounding units. Like instead of saying round to the nearest hundredths, you know, you could take that piece out or say round to the nearest tenths. And the kids won't pay enough attention if they're copying, and they'll put the rounding of the answer key. Yeah. So that's something I do every once in a while when I am afraid that stuff's getting handed down. I'll just change the rounding. I don't have to go through and change the problems. But I figure if you're paying enough attention that you notice the rounding has changed, then you've probably worked the problem on your own, and you're just referencing somebody else's work to kind of check it. But you can easily change that several times over a 3-year span. And make sure and just kind of catch kids, warn them off of the habit of, you know, cheating in there. I know Adam and I are kind of on this balancing act where we're trying to keep moving forward because we know that our time's limited with you guys, but we also know that for some of you guys, you know, we got people who are just starting it this semester because they're teaching it in a compressed schedule. We also know that we have folks who are just getting ready to start 2-1, and here we're talking about 2-3. So we're trying to balance that, you know, keep going forward and handing you stuff, but I know it's hard to care about 2-3 when you're, you know, trying to survive thermodynamics. So, but Adam keeps these things recorded. Thankfully, his technology skills are obviously higher than mine, so they can't even share my screen tonight. But that we'll keep kind of trying to balance that. The next unit that we go into is Unit 3.1, which is the control systems units, and it's where we're going to start talking about VEX and the VEX parts, and the 3.1 to 3.7. The 3.1 and 3.6 are the training units for VEX, and then 3.1.7. 3.1.1, 3.1.6 are the training. 3.1.7 is a small build, and then there is the big build, the activity that goes. That's the Marvel sorter. And so we're going to try and kind of balance that. But Adam, I think probably next time we're getting ready to start 3.1, the control system. So if you guys have unearthed those parts, it's not the build parts. It's going to be the cortex and the sensors and the motors and things like that. I'll send a note out and kind of let you know when Adam and I decide what we're going to do with that. But if those parts are out there for you guys and you want to play with those a little bit, that's where I think we're going to start our next meeting at. Okay. Does anybody have a question they want to ask versus type? Yeah. Adam, do you have anything else? We can keep going through some of these if you want, or
No, I think that's good. Someone else have a
you
question?
answer. Tricia, the answer to your question is the stress strain unit. That this activity is in 2.3, which is the materials and manufacturing, and material testing, and that's a different unit than 3.1, which is the control system unit. And so we don't really talk stress strain in unit 3.1.
Yeah, I know. I think Tricia, you were saying this is, or was it somebody else that was looking at trying to keep the big picture here? Yeah. One of the things that I think a lot of us always struggle with this course is it's not really a building course. So what you're used to in most of the classes that you teach is you start off with the basics, and then each unit, each semester, you're adding more and you're building up till they really have that huge big picture in the end. Because this class is meant to be a sampling course, it just hits all sorts of different fields and different directions. There are some overarching things like efficiency is something we do in almost all the units. We get into the design process in all the units, the teamwork, the engineering notebook, and the idea of engineering in general. But it's not like we do simple machines unit 1. Well, we never really bring them back, and that doesn't necessarily help them when they're doing, statics or something to that effect. But
And it's for that reason that I make quizzes over new content, and I make tests that have about 50% new and 50% cumulative. So usually my tests are part open-ended, part multiple choice. Really, the open-ended is so I can see what they're doing and give them partial credit. The multiple choice is because that's how their final exam is going to be. And so I use the multiple choice part to be a review of the previous units, because this stuff is so discrete that if I don't keep asking them about Ohm's law, then the only thing they'll remember is that it's my password to my website. So I continue to ask them questions on mechanical advantage and electricity and thermodynamics on all of my chapter tests on that cumulative component to it. So it's very, very, very discrete. I tell them it's like a tapas buffet. Like, you never get enough to fill you up. For my kids that loved electricity, they're sad when it goes. But for my kids who hated thermodynamics, it's not going to be here very long. So it's like Adam said, it's really a sampling course. So you don't fill up on anything. You just get to taste all of it. And my hope is that when they look at, when they're writing those papers and look at the college courses, for my kids, that component's coming up for them. They're going to do that in this quarter. And they see those college outlines of courses, they're going to see, oh, thermodynamics, there's thermo 1 and 2, I don't know what that is. Oh, statics and dynamics. And so they start to see words that they've seen before, and so it has some understanding to them, which is different than maybe like some of the other classes we teach. Did the trust question get answered?
I think so.
Okay, you have that? Okay. I break our bridges and stuff with just buckets of sand, to be honest, and then we just weigh them, just because of the stuff that we do versus using the SSA. But if just the little trusses themselves, I would use maybe the trust tester or a version of that you build with X.
Karen, I'm
Oh.
on your website, and I'm trying to figure out. You said I got the password and everything. If that any files that you have you're willing to share are on there, is that like under your calendar? How I'm looking,
Yeah.
engineering notebook, PowerPoint, or homework. But when I
Yeah.
click on like homework activity, it just says it's just like it's a schedule. So that's not something that's shared. Am I correct in
So,
understanding
like,
that?
if you go to my principles of engineering, you're on my calendar,
Mm-hmm.
you click on principles of engineering. If you
Yeah.
look at day by day by day,
Yes.
so if you go far enough, you'll see like my review. Homework will be
Okay.
review 2-1, and then it'll see
Okay.
click to view, and so that
Mm-hmm.
document is attached to
Okay.
that.
I understand.
And
Okay.
so
So if it
then,
doesn't say click to view, it's not a document.
right, and the PowerPoints
Okay.
are there for my kids to watch.
Right.
So those are attached.
Okay.
And most of the worksheets are anything that's a worksheet that they need is probably there.
Okay, I wasn't sure because I thought I'm trying to go back and listen to the old sessions that I was missing, and
Mm-hmm.
I thought you had said in the first one that since so many answer keys are kind of out there on the web, that you change a few numbers here or there, and I didn't know if you had that posted on your private website or if you just kind of
Oh,
change that and then give
the
those to
answer
the
keys
kids.
are the questions. They're just really
The
subtle.
question.
So like
Okay.
the assignment 1 whatever will
Yeah.
I'll just have edited the project lead the way assignment one
Okay,
or two
just change the
questions.
numbers. Okay.
Yeah.
Yeah.
Or change,
All right.
I tend to change the rounding or just change maybe 1 or 2 questions in there,
That makes sense.
just to keep it
Yeah, keep
fresh.
them honest.
Okay.
There's,
And something else is, am I supposed to keep all of these files private? Like we do everything through Google Drive at
Yeah.
my school. So I should like password and just give my
Hmm.
kids the username and password. Okay, that I wasn't aware of. Thank you.
but you have
Yeah.
your Google Drive is a dot whatever extension for your school, right?
No, I don't. Well, probably. I honestly don't know. I have to sign in using my school email if that's helpful, but it's public to the web.
If it's public to the web, like you know
Yeah.
how to get to my school, to get to my
Yes.
website, you had to have my
Yeah.
password.
Hmm.
That's the only way you are permitted to post anything Project Lead the Way.
Okay, then I'll put a. It's pretty easy, I think, to put a password on a folder. I'll just go ahead and do that.
Yeah.
Yeah, and that's probably at the beginning of the school year. Someone in your school signed a copyright and privacy agreement, and that I think is probably somewhere in this cohort at the beginning. Probably that document
Okay.
exists, and it just says that stuff won't be out there.
Okay.
Yeah,
All
I
right.
wish it was less out there than it is.
Yeah.
I spend a lot of time trying to get it off. But long and short, it's their own consequence. My tests aren't out there, so that's where that comes back around to get them. Anybody else? Okay. I think we are 2 weeks away. Adam, is that right?
Yeah, the 2nd, February the 2nd.
Okay.
And then
Okay.
we'll kind of play around with dates. We'll get back to you on, because I know a lot of people will be on spring break or something to that effect, and we'll try to work around that the best we can. If it doesn't work out for you and you're on spring break and you don't want to come, that's up to you. we won't hold it against you.
Exactly right. And I know some people have had some snow days. I think it was Bill said they're about a week behind because of snow days. So tonight's really the first weather stuff we've had, and it really just affected you guys, not my other students. So.
Cool.
Okay.
Well, have a good
Awesome.
2 weeks, and hopefully if everybody has good weather.
Yeah, be careful. Hey, Adam, can you try and share screens with me again so I can figure out what I need to push and see if I can